Previously on this channel, we've spoken about Intel, who's set to use machine learning on their 5nm product portfolio. A few weeks ago, Google published a paper saying that they're using machine learning to help develop their TPU AI processors. And I've recently spoken with Synopsys CEO Art de Gois about the future of machine learning compute. He's got 2 keynote presentations at industry technology conferences this year, so it was fun to hear what he was going to say about the future of machine learning with chip design. What's your minimum specification? Ever wanted to try and roll your own VPN, game server, or other web service for free? Linode makes cloud computing fast, simple, and affordable, allowing you to focus on your projects, not your infrastructure. Try Linode today with a free $100 60-day credit at linode.com/TechTechPotato. So before we get into the meat of this video, let's talk about machine learning just as a concept. What we have is an algorithm which contains a bunch of inputs, recognizes what to do with those inputs, and then produces a series of outputs. If you were playing a game of tic-tac-toe, for example, you would place one X on the board, and then the algorithm would decide the best place to put that O. Using weighted functions, and you use a trained algorithm that identifies all the different configurations. With tic-tac-toe, there's not that many. And then you can find, the best weighted result at the end of it. In terms of playing games, Google, with their AlphaGo team, developed machine learning for the game of Go, which has 361 different positions and is arguably more complex than all the atoms in the known universe. They trained machine learning algorithms to beat Grandmaster Lee Sedol in a 4-to-1 5-match series. The point is, machine learning is there when you can't brute force an application, when you can't brute force just through sheer compute, but you still have to train it right and have the right algorithms in order to get the result that you need at the end, such that when that algorithm is presented with new data, new environments, then it will produce the best of what it can do. Now, the desire for machine learning is at fever pitch right now. I've spoken with a number of AI companies who are developing silicon to enhance and speed up AI compute and training. The point is, there's a lot of economics behind this. We have lots of data that goes unanalyzed, and people are starting to realize the economic benefit of analyzing that data. If you can be proactive to your customers or reactive to your customers, there is inherent value in that. And people are being prepared to put money where their mouth is and develop the algorithms and the hardware behind it. Google has a line of AI machine learning processors called TPUs, or Tensor Processing Units. These are designed to help accelerate Google's workflow, and they've scaled now into their 4th generation. Similarly, Tesla's fully self-driving chip uses a bunch of AI hardware in order to be able to solve the vision problem of self-driving. And all of these chips have essentially been developed with a combination of human design and algorithmic solutions, sort of very equation static based solutions. So a modern engineer, a modern circuit designer, if you have one designer making that chip, they've got to place millions and billions of transistors, gates, and blocks. So in order to simplify the problem, typically these engineers will work on one specific area of the design, but they will also work with predefined units of gates, transistors, macros, sort of bigger building blocks, so they're not manually placing these millions and millions of transistors themselves. Then, once they have a design that they think is ready, which may take months to do, they pass it through some algorithmic software which determines where all the wires go, and then that will output expected values for frequency, for power. There's a whole range of software, simulation software designed to help with this. And to date, for the past, say, 35 years, this software has been more linearly, more sort of if-then, more that sort of programmatic. It's not really touched on machine learning in the same way that we consider machine learning today. So Google's paper, which actually came out last year but is been recently published in Nature with a few updates, what they've done is they've taken 4 different types of block inside their Tensor Processing Unit and put it through an algorithm that determines the best place to put those blocks, and also groups of transistors and gates. The search space for placing this sort of stuff is effectively infinite. When you place transistor elements on silicon in what we call a floor plan, the proximity of how those elements are to every other element and how they interact can vary based on physical location, can vary based on application. Are you going straight? Are you going over? It becomes very complicated, and as a result, the search space, the whole mathematical, if you tried every possible combination, we're talking about 10 to the 2,000, 10 to the 10,000. This is really number of atoms in the universe to the power of the number of atoms in the universe, and even more than that sort of scale. So what the machine learning algorithm has to do is it has to determine what works best in general with these high-level blocks. The algorithm is fed essentially what blocks are needed, how they interact, how they functionally interact algorithmically with other elements in the design, and then you program to minimize for, say, wire length, for power, for performance, for die area, depending on what optimization point you want. Now, the paper from Google, which you can find most of it online, showcased that they did 4 blocks. They compared manual placement with their in-house tools for placement versus their machine learning placement tools. And in pretty much every case, machine learning tools got better results. They were able to do it faster, in some cases less than 24 hours versus several months for a team of engineers. And, this got widespread coverage in the press. So why am I talking about that today, and what's changed since Google published that paper? So Synopsys reached out to me and said, hey, look, we've got the keynote presentations at 2 industry conferences this year. We've got ISSCC and Hot Chips. And if you guys follow the channel, I really like Hot Chips. And when I saw Synopsys on the keynote for Hot Chips, I was like, what exactly are they going to talk about? So Synopsys is what's called an EDA tool company, electronic design automation. Their goal, they have software to help with creating semiconductor silicon processors, chips. And if you want to make chips at some of the major foundries, especially on leading edge processes, you have a choice of 2 companies, and Synopsys is the biggest one. So, of course, being able to implement artificial intelligence and machine learning to helping chip design is key to the future growth of Synopsys. I spoke to the CEO, Art de Gois, pretty early on, ahead of Hot Chips, to ask what is this all about and what is Synopsys's vision on what machine learning can do with compute. Now, it's a pretty broad topic. I mean, machine learning, if you can find a way to implement it into your design toolchain, it sounds like it's a magical tool, right? Instead of having a group of engineers work for 6 months and you may get, several optimization points that they come up with, being able to put the same, restrictions into a system that runs overnight or across, hundreds and hundreds of systems, you'll end up with hundreds and hundreds of different optimization points depending on how you want that product to go. And it turns out that they end up being a lot better than what humans can do. And that's with untrained algorithms that just understand how placement goes. Whereas with the pre-trained algorithms, they even go a step beyond. Now, I had a number of questions to this. Synopsys is still kind of fleshing out what exactly they want to present at these conferences. And so I suggested, started talking about roadmap. I mean, it's great that you're putting machine learning into silicon design, but where's the roadmap here? What do we get as we go forward over the next 10 years with this technology? It's one thing just to speed it up. I mean, yes, getting 100,000, 10,000 solutions to your problem is great, but if that's artificially limited by the algorithm itself in some way, is there a roadmap to help develop with that? I also asked about the concept which actually came up in the AlphaGo game that I mentioned before. In that series, if you followed it, you'll know that both the human player and the AI player made a 1 in 10,000 move that was unexpected.
This is the hinge of the game.
Look at that move. That's an exciting move.
Whoa. Oh, that's going to change things.
So that's a really exciting move, or a very sharp move by Lee Sedol.
Now, there are arguments there that humans are more likely to make those 1 in 10,000 moves than machines, because humans are ultimately more variable and have directed variability, where sometimes machine learning is less directed variability. So in the instance where some of these programs can produce, a halo design out of the restrictions and the inputs you give them, what are the chances of that actually happening inside this machine learning? And I think the final element to think about this is within the abstraction layers. Google, as presented, was fairly limited in how they presented their machine learning. It was simply on 4 different elements of the TPU. It wasn't the whole TPU chip, because that would have too many degrees of freedom. However, the goal of this software is to build out to that full chip design. So the question here is, do we just apply the machine learning to the big blocks? Or is there a way where sometimes the smaller blocks make sense? When humans design chips, they work with a very limited number of features and then essentially scale them up. With AI, we can now expand what was maybe sort of 10 or 12 different, say, flip-flops or gates, and make that into maybe 1,000. And then the algorithm, the machine learning, can work on the thousands to get the best result rather than what the engineers were limited by. So I'd be interested in to hear how Synopsys intends to kind of push the boundaries of what are considered very typical abstraction layers in that regard. If you've watched my Jim Keller interview recently, you'll know we spoke a lot about abstraction layers in the concept of humans, though how it permeates through machine learning is still an open-ended question that I think a company like Synopsys should be well poised to answer. I also mentioned the same question I actually put to Jim, actually. At what point do these processes, what comes out of machine learning, become completely unfathomable to human engineers? Will we ever be able to derive value and complexity out of these machine learning designs that we can then fundamentally readjust our baseline? Jim said that having those sorts of processes are pretty much here already, if not, in the next few years. He said there are parts of the modern processor that already use small amounts of machine learning that are that level of unfathomable, though to have it across a whole chip is going to be an interesting topic as we move forward. So if you're interested in catching a talk by Synopsys at Hot Chips, it'll be August 22nd to 24th. I think they're on the 23rd at about noon Pacific. Sign-up's really cheap. As I said in my Hot Chips video, highly recommended for anyone in the industry who's interested in processor and processor design. In the past few years, we've also had AMD and Intel and TSMC do their keynote presentations. So to have somebody on the EDA tool side of things, I think it's going to be quite interesting. Many thanks if you enjoyed this video. There's a like, there's a subscribe. Please leave a comment on where you think machine learning is going to be. You can also follow me on Twitter @Cutress, or there is a Patreon, patreon.com/TechTechPotato.